So hello friends, welcome back to our channel STM Mechatronics. In this video we will see how to interface ST7735 TFT display with STM controller. So in this video we are going to use a blue pill board and a ST7735 TFT display. Okay, you can make these connections as per this diagram. Now the connections from controller to the display are like this. So PB0 is used as a reset display pin. PB1 is chip select for the display. PB3 is SCL, the clock pin. PB4 is data or command, the selection between data or command, and PB5 is SDA. So these 5 pins are necessary, which needs to be connected to the TFT display. Okay, we have kept the reset pin as it is. We have not connected it to display. The between controller and between the TFT display there are only 4 pins, that is CS, then clock, chip select, clock, data. These are 3 SPI pins, and data or command. Okay, so these 4 pins are connected between the controller and the display. Okay, rest of the pins like D from D1 to D17, it is connected to ground, and external pins, these are connected to either VCC or ground. From here you can see the connections. Okay, now we are using a blue pill board. So first what you have to do is you have to go open your STM Cube IDE, click on file, click on new, click on STM32 project. I have already created my project, but I'll show you the initial steps. Okay, so over here you have to type STM32F103C8 controller. That is a blue pill board. Okay, after you click here, you click over here and click on next. So that's how you are selecting the controller. Now give the project name. I have given my project name as TFT display interface with STM32F103C8. Right, the target language you have to keep it as C, targeted binary executable, and target project type STM Cube IDE. Okay, and then you have to click on finish, either next or finish. Okay, that's that way your project will be created. Now you will be directed towards this pin configuration view. Okay, now in pin configuration, which pins we have to configure is PB1, PB3, PB4, PB5. So from PB0, 1, 3, 4, 5, it is not, 2 is not connected, PB2 is not connected. Okay, so PB0, 1, 3, 4, 5, and 1 pin connection, GPIO pin connection to the LED. So total 6 pins we have to configure as GPIO output. Okay, so PC13 is connected as GPIO output. You have to click over here, GPIO output. Then PB1, PB0, PB1, PB2. PB2 is not connected, so we can clear the state. PB3, PB4, PB5. Okay, so there are total 6 pins that we have configured as GPIO output. Now going over here in GPIO output, right? So over here the GPIO mode is output push pull, internal pull up is enabled, and the maximum output speed we have kept it as high. Okay, and the initial state of GPIO pin we have kept it as high. So this configuration you have to do for all the pins, all the GPIO pins. Over here you can see I have kept the configuration same for all the 6 GPIO pins. Okay, now in RCC, right, I have kept the high speed clock HSC as disabled, low speed clock as disabled. Okay, now coming to the clock configuration, I have not configured any of the external peripheral, I have not configured any other peripheral than the GPIO. Okay, so you have to keep it as it is. Now coming to clock configuration, we are using the internal HSI, that is RC clock oscillator, RC oscillator, okay, but we are using the PLL. So our 8 megahertz RC oscillator will create a system clock of 64 megahertz using this PLL loop, okay, phase lock loop. So we are in the PLL clock source, we are selecting the HSI, then we are giving like the PLL multiplier as 16, okay, and over here in the system clock marks we are selecting the PLL clock. Now these settings you have to complete, okay. Rest of this divider, right, this multiplier and these dividers you have to keep as I have shown it to you, okay. Once this is done, you have to click on generate the code, okay. So I am creating the code in front of you, okay. Like once the code is generated, right, I have added additional functionalities for our display to work. In order to generate the hex file, what you have to do is click on the project name, then click on the properties, then go to C++ build. In that, click on settings, right. Once this tool settings window is appeared, you have to click on post build outputs, MCU MPU post build outputs, and in the convert to Intel hex file you have to tick it, okay. You have to check this box. After that you have to click on apply, right, and apply and close. So this way you are like, once this is enabled, you will be able to generate the hex file, okay. Before I start to explain this code, right, what it is doing, how it is working, right, I'll show you the output what we are going to display on the TFT display. So initially there will be a black screen, then there will be a white screen, then it will be filled with black color, again it will be filled with white color, okay. Then we have created a pattern of the red lines. Now you can see that the pattern is getting filled up from the bottom corner to top, but now you can see that there is a slight color change from black to reddish, right, but it is getting filled from top to bottom. So all this we have done in our code. We will understand like one by one how we are achieving this functionality, right. You can see that the solid colors are getting filled up from top to bottom, then these lines are getting filled from bottom to top, right. There is color change from a solid black to something reddish. The color reddish color in the red color intensity is increasing in the loops, okay. The red color intensity is going on increasing, okay. As you can see, the red color intensities are going on increasing. Now this is the output that we want to create, okay. You can create any different output, any different color. So now we will first understand how I have created this code, okay. Then now you can do slight modifications in that code and achieve your functionality, okay. So going to the main code, I'll first show you the whole code, okay. So there will be no ambiguity in your understanding. So from main.h, from first line I am showing it to you. What I'll do is I'll increase the size of the text editor, typing, text editors. S12, click on OK, click on apply, click on close. Right, so starting from first line, right, this is main.h. In the user code in begin includes, I have included my SPI-TFT display.h. This file we have written it ourselves, so we are including that file. I'll show it to you, the contents of that file. Okay, then these are the code generated files, system clock config and max GPIO. In the int main, we have used one variable uint32 color. The initial value of color is 0. Okay, then hal init, system clock config init. Okay, then mx GPIO init. Now these are the user defined functions that we have written. Okay, we will go through this one by one. Now in the while loop, so okay, over here I'll come over here. First function is display reset, second one is display sleep out, third one is display set column mode. Okay, fourth one is disp set mat ctl top to bottom, fifth one is display on. Okay, now here you can see that I am again using the same function top to bottom. Okay, then display image, then the color, this is total white. Okay, then from bottom to top, then display image 1. Okay, then I'm increasing the color value from 10. Okay, then I'm toggling the LED pin. So this is the sequence that we are doing. So from top to bottom it will be filled up with black color, the image color will be displayed, third will be white color will be displayed, fourth one will be the pattern, red line pattern will be displayed, after that the image will be displayed. Okay, likewise we have doing again, the color intensity will be increased. Okay, the PC13 will be toggled. So after this PC13 will be toggled. Right, again color is getting filled from top to bottom. Right, after this white color will be filled from top to bottom. Correct, after this from bottom to top the red line patterns will be filled. Okay, and after this the PC13 will be toggled. So that is the sequence that we are doing. Right, so this is the sequence that we are doing. Okay, this is system generated, so I am not going through this. Again max GPIO is system generated. Okay, and then comes the error handler. Okay, this is the overall code, overall main.c file code. Now I have, like, in the initial lines I have included that this SPI-TFT display.h file. Okay, now we will go through the contents of the SPI-TFT display.h file. In core, in includes, okay, I have included this file SPI-TFT display.h. Okay, now over here you can see that I have defined the pins. Now which pin will be connected to which port and which port pin. Okay, so over here I have declared the port pins. Okay, basically which port, either it may be GPIO port A, GPIO port B, that port I have defined over here, and over here which port pin it is connected. So for reset it is GPIO 0, for chip select it is 1, for SDO it is 5, for clock it is 3, for data command it is 4. Okay, likewise. Now display command width is of 8 bits. Okay, now I have created one enumeration. Okay, this is similar to the this is very much similar to the structure that we create in C language. Basically enumeration gives the value, user defined values to the variables. Okay, so for no commands it is 0x00, for write to display it is 0x06, For sleep out it is 0x11, for normal mode it is 0x13, for display off it is 0x28, for display on it is 0x29, and likewise. So these are the display commands. Now you will be having this question that from where I got this, right? From where I got these hex values. So you can go to the data sheet basically. Okay, I'll type as let's go to normal. For normal mode or for display on we have 29, right? So I'll check over here 29H, right? Sorry. So over here you can see that this is the system function command list. Okay, so yeah, it is for no operation it is 0x00, for software reset it is 0x01, for read ID, okay, read device ID or read display ID it is 0x04, right? For read display status it is 0x9H, for read display power it is 1H, right? Likewise, so I have told you that for display on it is 29H. Here you can see that for display on it is 29H, for display off it is 28H. Okay, for inversion on it is 21H, for inversion off it is 20H, for normal on it is 13H, for partial on it is 12H, for sleep out it is 11H, for sleep in it is 10H. Okay, likewise you can see the various command and its numbers. Okay, and you can add those commands in this enumeration. Okay, later we can use those enumeration. For second thing like display and command, we have used another enumeration type enumeration command or data. Okay, for display command we are using 0 and for display data we are using 1. Okay. And these are the functions, user defined functions. So these are the declaration of the functions that we are defined in SPI-TFT display.c. Okay, so from starting of the file I'll show you. I'll slowly go one by one so that you can check the lines. Okay, I'll go very steadily. These are two clocks, SPI clock high, clock low. Okay, SPI data high, data low, then SPI clock. So this is giving the clock pulse basically. Then SPI data, then display reset, display active, then chip select enable, chip select disable, then the delays, delay, then select command or data, then the display initialization, then send command. This will be very much useful function. Then send data. Okay, then display image, then display image 1, then display screen color, display sleep out, display normal mode on, display off, display memory write, display inversion on, display inversion off, display select column mode, display select CA, display select array. Okay, now MAD CTL is memory data access control. Okay, then display set column mode. Okay, so these are the user defined functions that we have written in this file. Okay, I provide this file along with the code, only this file. Okay, if you are, I'll only provide this SPI-TFT display.c file. Okay, now we'll come to the main.c. So you understood, like I have see. Now coming to this .c file, right? SPI-TFT display.c file. I used three variables. This is pixel red, pixel green and pixel blue. Okay, now we are using our TFT display in 18-bit mode. Okay, now out of if we consider the 18-bit mode for one pixel, right, what it means is for each pixel we are sending total, if we divide 18 by 3, right, then 6 bits we will be sending for each pixel. Okay, but the thing is that out of 8 bits, right, we are only using 6 bits for one pixel, right. So those two last bit 0 and bit 1, those are don't care. So whatever data we are sending, right, 6 bit of data, we have to shift it to left by 2 position. Okay, so that we have to consider, that I'll show it to you. So for pixel red, pixel green and pixel blue, we are using one variable of 8 bit. Okay, 1 byte variable we are using. Now this is color counter and this is get data, global data. Now we will go one by one. Okay, so this is SPI clock high, right. So what we have to do is we have to do the clock pin high, right. That is very much straightforward. We are using the HAL libraries for doing this. We are setting the clock low. Okay, now similarly for data, we are setting the data high and we are setting the data pin low. Okay, now we have to give the clock pulse, right. So for giving the clock pulse, what we do is we raise the clock pin to logic 1 and then after some delay we raise it back to clock pin low, clock 0. Now in between there should be some delay, right. So I have provided this NOP operation. This is very much assembly language programming. Okay, so one clock cycle in which it will do, the controller will do nothing. Okay, so this is NOP operation. But after reset I have not used any NOP instruction. Why is that? Because whenever function calls this SPI clock, right, there will be some calling overheads. Okay, and those calling overheads will generate some delay itself. It might be of 2-3 clock cycles, right, the controller clock cycle, system clock cycles, or greater than that or required that. Same back from returning, while when the program counter is returning from this function back to the original state, right, at that time it will be also have some delay. So that's why I have not added any NOP instruction after bringing the clock pin low. Okay. So data pin high, right. So whatever data pin state it is, either 0 or 1, we are using it to set it to the data pin. If it is 0, write it 0. If it is 1, write it as 1. Okay, now display reset. Okay, for display reset, currently we are not using this display reset functionality or pin in our programming, but I have written the code for future reference. Okay, so the reset pin we are bringing it to low. It is active low. Okay, the RES reset pin is active low. That's why it will be tied to logic 1, right. To reset the display, what we have to do is we have to tie it to logic 0. Okay, so we are bringing it to down, we are bringing it down. After some delay we are again bringing it up. Now this HAL delay of 120 millisecond, right, HAL delay is used for generating the millisecond delay. You can see over in the description, right. This function provides the minimum delay in milliseconds. So HAL delay is of 120 milliseconds. Now this 120 milliseconds, it is already defined in the data sheet. that you must give 120 milliseconds of time for the display to completely reset it, right? And for the VDD and VDDI to properly set up, okay, or to get back to the proper voltage levels. Okay, so for that 120 milliseconds are necessary. That's why we have given the 120 milliseconds of delay. Okay, same for display active. Again, this reset pin we are setting it to logic 1. Okay, now chip select enable. Now chip select enable. Again, the CS pin is active low pin. So to enable the SPI TFT driver, right, we have to bring the CS pin to logic 0. So that we have done is so that we have achieved using this functionality. Okay, HAL GPIO, right, bring CS pin to logic 0. Okay, now if you want to deselect the TFT driver, right, chip select disable, we are setting it to logic 1. Again, this is very crude delay. Okay, set data or command. Okay, depending on whether it is data or command. If it is 0, it is command. Okay, if it is 1, it is data. Now this is the initialization sequence. I'll explain this in the next videos, but not in this current video. Okay, so whenever we are sending the command, right, so first thing what we have to do is we have to on the like D or CS pin, right, on the data or command pin, what we have to do is we have to send 0 for command and 1 for data. So here we are sending the command. So right, so for display command, this enumeration, it is the value of 0. Okay, so we are bringing this pin to logic 0. In this way we are sending, like whatever data we are sending, it means that we are sending the command to the display. Okay, now we are sending data, right, 8 bit of data, so it is 80. Okay, now bit by bit we are sending the data. So in the first iteration, this for loop will run for 8 times. Okay, if you see, display command width is of 8, its value is 8. So the loop will start from 0, it will come till 8. Okay, and it will increment till 8. So this for loop will run for 8 times. Okay, now this global data, the initial value of global data is 0. Okay, anyways it doesn't matter for the initial whatever the initial value of G data is, because we are overriding that with this operation. Okay, so the whole value, whatever the previous value, it will get replaced by the new value. Okay, in each iteration. So command code, now this is the command code that we are sending. Okay, command code and data shift bit, the initial value of data shift bit is 80. Okay, before this for loop starts. Now command code and 80, so it will give us the MSB, value of MSB. Okay, most significant bit, whether it is 1 or 0. Now we are shifting, we want to send that MSB, right, to the GPIO pin over the like SDA pin, right. So we are shifting it 7 times, right. The initial value of loop in first iteration, it will be 0, right. So 7 minus 0, 7. Now this data, it is shifted 7 times. Okay, so the MSB that is on D7, it will come to D0, or bit position 7, it will come to bit position 0. Okay, now if it is 0, right, or if it is 1, then we are setting the pin. Now which pin we are setting? If you see over here, we are using GPIO port B. This is bit set reset register. Okay, BSRR is bit set reset register. Now we are ORing with this to to 20H value. Okay, so 20H comes as in the binary form if we write it as 100000. So it is PB0, 1, 2, 3, 4 and 5. So we are setting the PB5. Okay, so PB5, if we check, it is SDA pin, right? PB5 is SDA pin. So we are writing that MSB on the SDA pin. Okay, while this data or command pin is logic 0, tied to logic 0. Okay, so the MSB is sent. If this G data, whatever command we have sent, if this G data becomes 0, then that means we are sending 0. Okay, 0 on that pin. So what we have to do is we have to clear that first previous part, right? We have to first clear this previous part. That way we have, what we are doing is, like, we want to clear the PB5, right? So for clearing PB5, what we are doing is we are ending with this value. We are keeping the rest of the pins as it is. We don't want to hamper those, but we want to clear that. So here we are ending with 0. Anything ended with 0 results in 0. Okay, and anything ended with 1 results in that bit. Okay, so that's why we are only resetting PB5 in the BSRR. Okay, now the lower 16 bits, right, those are used for setting the bit or GPIO port pins, and upper 16 bit are for resetting the GPIO pins. So if you see, right, these 4 zeros we have written, and this same 220H value we have likewise shifted by 16 times. Okay, so in this way we are resetting the PB5 pin. This 10 value, if you see the difference between this value and this value, right, it is shifted by 16 times it is shifted left by 16 times, right? So in that way, first what we are clearing is PB5 bit set value, then we are resetting it. Okay, so in this way we are sending 0. So for this is for sending 1 to PB5, send or set PB5 to logic 1, right? And here set PB5 to logic 0. Okay, now after doing this, right, what we are doing is we have to give the clock pulse. Now if you see, right, for clock we are using PB3. So same way what we have to do is we have to set the third position 0, 1, 2, 3. This means 80, right? Sorry, 0x08, right? So in GPIO BSRR we are ORing with value 0x08. So this way we will set PB3 to logic 1. Okay, after giving some delay, right, and performing some shifting operation. Now this shifting operation is for getting the bit number 6, right, value of bit number 6, whether it is 0 or not, right? So from MSB we are first sending MSB, then MSB minus 1, that is if we are sending bit number 7 as first, then we will send bit number 6, then we will send bit number 5, then we will send bit number 4, and in last we will send bit number 0. Okay, so that's why we are doing the right shift operation. Okay, now this will give some delay, these two operations will give some delay, right? After that again we have to bring the PB3 to logic 0. Okay, so for that we are first clearing the bit 3 in this BSRR register, then we are setting this bit, right, means bit number, this is bit 16, 17, 18, 19. We are setting bit number 19 to reset the PB3. Okay, so it is like giving a clock pulse. Okay, then here it ends the send command function. Okay. Send data function is very much similar to the send command function. Just one small difference is over here. You can see this display command, right? The data or command pin, it is set to logic 0 for command, right? And in send data, the data and command pin, it is set to logic 1. So if you see the display data value, this enumeration value, it is 1, and for command it is 0. Okay, so that's the only difference between those two functions. Rest of the functionality is exactly similar. Okay, now we will come to display image. To display image, what we have to do is we have to first select the display data. So we have to set this CS pin to logic 0. Okay, so we have done using the HAL pin. Now send command, right? 2CH, we will check over here, right? So 2CH is for RAM write, right? Memory write. So first thing what we are doing is we are sending 2CH and then we are sending the data. Okay, so first thing we are doing is we are sending the command, that is memory write. This is memory write command, right? This is memory write command. Then what we are doing is we are setting the pin, this data or command pin, that we are setting it to data. Okay, now why I am doing that? Because over here you can see this, right? This data or command pin must be set to 1 before sending the data. Okay, and before like the sending the command, it should be 0. Okay, so before the display image it is sent, right? What we are doing is pixel read, right? We are shifting this value by 2. We are left shifting it the value by 2. So I have mentioned you right earlier that in LCD, in TFT display, from bit number like 7 to bit number 2, only these 6 bits are used. Okay, 6 bits are used. Okay, bit 1 and bit position 1 and bit position 0, those values are ignored. Okay, so in every pixel value, like bit number 7 to bit number 2, these values are used. Okay, so that's why we have whatever value is there, we are shifting it by 2. Okay, and then we are storing it into the local value. Now our display is of 132 into 162 pixels. Okay, so we are running this loop this many number of times. We are sending the value of each pixel. Okay, now if you can see that for each entire pixels of the display, we are sending the same value, exact same value. Okay, first we are sending the pixel red value, then we are sending the pixel green value, then we are sending the pixel blue value. Okay, we are sending the values again and again and again. So basically what we are doing is we are sending 132 into 162 into 3. Why 3? Because each pixel value is sent one by one by one. Okay, that's why. Then what we are doing is we are sending the command 0x06 after sending the data for each pixels of the resolution of 132 into 162, right? We are sending the command 0x06. Now 0x06 value, it is for display on. 0x06. write to display. This is the value that we are sending. Okay, so we are sending that write to display. Okay, then we are bringing this CS pin, chip select pin, to logic 1. Okay, now what we are doing is, this is the global variable. Okay, we are increasing the red pixel value by 10. Okay, once it reaches 3F, right, then what we are doing is we are resetting that value, we are increasing the green pixel value. So first red pixel value will be displayed, after that green pixel value will be displayed, after that blue pixel value will be displayed. Okay, increased. So likewise. Okay, now in display image 1, what we are doing is again selecting the display. Okay, sending the command, that is write to memory, right. This is 2C, same, write to memory. Okay, this is same, write to memory. Then what we are doing is we are setting the data. Now pixel red is FCH, FC stands for, so 1111 and 1100. So last 2 bits, as I mentioned, it is ignored, that's why we have kept it as 0. Okay, now what we are doing is pointer end y, pointer end x, end y, end x, end2, end2, this and this. Okay, now what we are doing is like if, right, this loop is ran 162 times, so 162 is the number of rows and 132 is the number of columns, right. So loop, right, this loop value, if it matches with loop into 161 divided by index is 132, 131, right. So if it matches with this, then send data pixel red. Okay, else send the data 000. So you have seen this pattern, right. After this you will see one pattern, right. So if you are seeing this pattern, right. So in this pattern what we are doing is, if this pixel, right, so if this pixel into this pixel, right, into 131, whatever the value is, 130, either 131 or 80 or 40, right, or this, right, or reverse order, right. So if it matches this coordinates, right, what it will do is it will display red, otherwise it will display black, right. So you are seeing this, it is display red, else it is display black. Okay, so just to show it to you, we are sending FF. Okay, send data FF. I'll compile this. Okay, now instead of black it will be seen as, so instead of black it will be seen as white pixels, right. It will start from over here, it will come to this, then it will start from white from top to bottom, right. From bottom to top it will start like this. Okay, I have made some mistake, but yeah, we'll correct those. Right now let's send the pixel value as red, it is FCH, right. Data is, else it is 000000, right. So what we will do is we are filling the value as ff, right? Then what we will do is we are sending the value as ff and we are sending the value as ff. Okay, so this will make the display as white. Okay, okay, so again we have made, I guess, one mistake over here. So the blue pixel value and the green pixel value and the red pixel value, these are getting equally off, on and off. Okay, so what we can do is we'll simply keep it as this. Okay, right now we'll simply keep it as this, else what we'll have to send some another value. Okay, but yeah, so after that again we are sending 0x06 write to display command. Now coming to main, display reset, it is fairly simple function. We are setting and resetting the display. Okay, display sleep out, this is for this we are using 11h command. Okay, all these commands you will get in the datasheet. Set column mode. Okay, for setting the column mode we have to use this command and then we have to send the data. Okay, for this 0x06, why we are sending, we have to set it 18-bit per pixel, right? And for that the IFP bits, right, IFPF bits value we have to set it as 110. Okay, so that is inside this data sheet that you can see. Okay, then from top to bottom, right, we have to set it as 00, and from bottom to top we have to set it as 11. So like from going on in the datasheet you will understand. Now display image, I have already explained this function, right? Then display screen color, right, the whatever color that we are sending, right? First we have to shift it by 12, right, to get the red pixel value. Then we have to shift it by 6 to get the green color value. Then we have to shift it by and with FC0 to get the blue pixel value. This is fairly simple code. We are again repeating this same loop for 162 into 132 times, right? This is because 132 are the columns and 162 are the rows, number of rows, right? Then we are sending the each pixel value, either red, green or blue. Okay, then we are sending the write to display command. Okay, so this is again fairly simple. Okay, then coming to bottom to top, right, for this we have to set mx equals to 1, my equals to 1 and ml equals to 1. Okay, these are the bits. So now coming to display image 1 function. Okay, so this function we have gone through. Okay, and after that we are increasing the color value. This is the global variable. Okay, so in this manner this function works. Okay, now what we will do is we will tweak some things, right, that I told you that in the display image 1, right? So what we will do is like send data pixel rate data, right? what we will do, we will send this over here 0x00 and over here 0x00, but here, right, what we will do is we will send data as ff and ff. So now let's try this. Basically what it should do is, so earlier what we were seeing the red lines on a black screen, right? Now we should see red lines on white screen. Right, so you see that we have tweaked some things and we got this inverted, right? But yes, this is the code that we are using. Okay, and in next code we will see like these display inversion on and off things, right? Now in this video you can see that the display, it is not very much fast because we are using the HAL library. We are bit banging, right? We are using the GPIO functions to toggle the pin to generate the clock, right? But what if we are using the dedicated SPI peripheral of the STM controller? Okay, so that we will see next time in the next video. We'll obviously improve our coding little by little so that it makes a good sense, good programming. Okay, that we will do in the next video. So thanks for watching this video. I hope you like my explanation. So if you like my explanation, give it a like, share with your friends, and we'll see you in the next video.